I'm going to talk for a few minutes. Right, so enzyme catalysis, once again, it's just a biological catalyst is an enzyme. Okay, so it means it should be neither consumed or, well, it shouldn't be consumed during the actual reaction. Now, it may have a covalent attached intermediate, but you always get your enzyme back if it's a true enzyme. Okay, and then just to review, these are the two thermodynamic equations. It's important that free energy is equal to change in enthalpy minus T delta S, the change in entropy, and that this is the one that's really important. The delta G here, and notice it's got that little special dot and the asterisk, which we used to say not prime, or whatever, which that's what we always called it. That means it's at physiological conditions. Because if you think back to Gen Chem, there were standard conditions, and they use that little circle, the little circle that we call them knots. I don't know if that's a technical term for it, but the little circle part, which for general chemistry, that was like 1 molar concentration, 25 degrees Celsius, and 1 atm pressure. But in biochemistry, that doesn't make sense because our body's not at. For example, the easiest one is our body's not at 25 degrees. What's our temperature biologically? Pardon? Well, it's in Celsius, but what is it? What is the body temperature? 37. Okay, and so the biochemical, so that little prime and the knot together means it's under biochemical ones, which you'll find out. I think we really go into that more next semester, where it's 37 degrees. It's not 1 molar of everything. It's pH 7, which makes sense because if it's 1 molar concentration of hydrogen, that means it's pH 0. So which you're never at pH 0 in vivo. So it's pH 7. It's 37 degrees. It's either 1 or 5 millimolar magnesium, because magnesium makes sense. You have to have magnesium in vivo. The pressure is 1 atm, so same pressure. But that just means under biochemical conditions. That's what that little prime means. But once again, its free energy is equal to minus RT natural log of any thermodynamic equilibrium constant. Okay, we actually already covered this, how it doesn't change the amount of reactants or products that you have at the very end, because the delta G overall stays the same. The only thing that's changed is this activation energy whenever you do any type of catalysis. And in particular, when we talk about, when we talk about enzymes, it doesn't change your initial or your final end. It just changes the path by which you get there. Okay, and so that's what we're going to talk about. And that's what this is showing. I actually don't care for this because I think this figure ends up confusing some people. And so we have here, this is what this means. We have in the beginning, we have enzyme plus substrate. It binds the substrate to make this ES complex. That ES complex also has a fancy name called Michaelis complex, after Michaelis-Menten. Then, many times, it becomes a product, and it's still bound to the enzyme. And then, at the very end, you get your free enzyme plus your product. But overall, the initial and final states are the same, but it's just this pathway that's changed. What I don't like about this one is it shows as all of the tops being about the equal in energy and all the minima being the same in energy, and they may not be. Okay, so you may have some hills bigger than the others and some valleys lower than the others. Okay, but that's just the energy diagram. So for example, you could have something that looks like this. Okay, and so you always have transition states between each step, and you always will have a minima for whatever the product is for each step. And so here, the way that I have it drawn here, the ES complex is actually lower in energy than the EP complex. Okay, but in the uncatalyzed, it could have looked something like this. And so overall, it's still more catalytically active. No, it's faster because the big hill is now much smaller.
So that first dip is always going to be ES and
Right. That's for a simple mechanism. So there are some mechanisms that become more complicated. So for example, what if you have E plus the first S that has to bind, which has to then bind another substrate, a different substrate, which then makes the product. This is a combination. Like when you're taking two smaller things, you're making them together. It makes the product. So then, in this example here, we will actually have 1, 2, 3, 4 different ways. And I don't know what it would look like overall, but you'd have the beginning, you have an ES, ESS, EP, and then product. So that's why I'm saying either always for every step along the way, you're going to have a transition state and a minima. Okay. We've talked about this a little bit in the past, where the two far models, the two extremes for enzyme catalysis is called the lock and key, which has been disproven because it doesn't take the complementarity into, like the actual complementarity into account. And I'll explain this even better later on when we look at NG models. But it literally means like you'd have like a lock and a key, and so the substrate would be the key that goes into the enzyme lock, and everything would be fine and dandy. It had perfect complementarity. However, if that's true, then it would never want to leave. So instead, there's this whole idea of there's an induced fit where the substrate binding upon it, or sometimes some other type of effector binding, causes a change in the shape of the enzyme to make it more complementary to the substrate. And we're going to actually talk about in greater detail how this one isn't exactly 100% correct either. All right, and so that's where I want to end right now. But before you leave, I want everybody to take out a sheet of paper.